Hello, you're welcome. All right, so now the topic is electric potential. Okay, so now we're gonna start by defining the term electric potential. Okay, now electric potential at a point is defined as the work done in moving a unit positive charge from infinity to that point. Okay, so when a charge is moved, a unit positive charge, okay, the unit here, the unit positive charge is the unit positive charge is like a reference, okay, as the charge that is actually being moved. But that's by the way, okay. So now the work that is done in moving, let's say there's a point A. Now, anytime you have to evaluate electric potential is respect to a particular point. Potential at a point, okay? So we simply means that we are looking at the work that is done in moving a charge from infinity. Infinity is just like nowhere, okay? So we simply means that if there's a charge is actually moved to this point, okay? I can just reference that the charge comes from infinity, right? So the work that is done in moving a charge from infinity to a particular point, it is what is known as electric field, electric potential, right? And of course, because it's called potential, it has the symbol V, okay? The same V that is used for potential difference that you are familiar with in electricity, okay? So please take note of that. And of course, this is the foundation of that that's quantity. All right, so now we are going to actually derive a formula for this, okay? So we say that electric potential V is the work done. Okay, let me use W to represent work. Okay, work done in moving per unit charge, okay, or moving a unit charge. So that is work per charge, W all over Q. So please take note of that, all right? So this is the formula for electric potential, work per unit charge. One formula of it, okay? And of course, we know that the SI unit, the unit of electric potential is volts, okay? So please, volts, this is SI unit, volt V. All right, so now this is one formula, okay? I was still gonna give you another formula for electric potential. We'll derive it, okay? So now look at how it goes. For work, you are told that in physics, work is force times distance, okay? So I'm gonna do force times, since what we use for distance in electrostatics, static electricity is R, okay? So I'll do F times R, okay? So F times R. Then of course divided by the charge Q. All right, so let's go there. I'm going to now apply the formula for electric force, which of course you know that it is KQ square, okay? Q1, Q2, of course, Q square, Q times Q is Q square, right? Then of course multiply by KQ square all over R square. Hope you can still remember this is the formula for force, right? Then don't forget that the force is being multiplied by R. Okay, then all is divided by Q. The whole of this. Okay, you know already the whole of this is force, right? The whole of that is force. Let me separate it so that you know what I'm doing. All right, the whole of this. Okay, then times distance. Force times distance divided by charge. Okay, so now let's start our division. Okay, R cancel itself. Okay, 1, then cancel R square, have just R in the denominator here. Q square cancel by Q, just have Q at the numerator. So I will be left with just KQ, because this Q have cancelled, okay, one factor of the Q, right? Then of course this R have cancelled one factor of the R, so I'm left with just R. Okay, so this is another way of actually writing the formula of electric potential. So this formula number 1, you can use this. There's some cases where you need to use this, all right, or use this. Okay, so please take note of this. V is equal to KQ all over R. Okay, don't forget that previously we looked at E being equal to KQ all over R square. So now the V is equal to KQ all over R. Okay, so just know the difference. All right, so I think we are gonna let's see if there's an example. Okay, so the question that we need to apply. Okay, So now I have some question. I'm gonna bring it up. Okay, here we go. Okay, so the question goes like this: what is the electric potential at 2 meters from a charge 4 microcoulombs? Okay, so we have V. Okay, the charge is 2 meters. Is the point I'm looking at is the electric potential at the point which is 2 meters from the charge 4 microcoulombs. Okay, so now we are going to apply the formula KQ all over R. Okay, so which of course is our K, 9 times 10 as a power of 9, right? Then multiply by the Q, which of course is 4 times 10 raised to the power of minus 6. Okay, all right, divided by the distance 2 meters. All right, so just this is very easy to calculate. Okay, so no need. This is gonna be 4 divided by 2 is 2 times 9, that's 18. I'm having 18 times 10 raised to the power minus 3. Okay, so which of course is 0. Okay, that should be 0.18 volts. All right, so I hope that's well understood. Let's proceed. Okay. Okay, okay, there's a mistake here. Please pardon me. This is 9 minus 6. Okay, this is just, it's not minus 3. Okay, so it's 3. So which now makes this 18 times 1000. That's 18,000 volts. 18,000 volts. Okay, so that is it. Let's proceed. Okay, so now we are going to look at this. Okay, we are going to look at a situation where you have system of charges. Okay, electric potential due to system of charges. System of charges is not just one charge. Okay, many charge. Remember, when we define electric potential, we are looking at electric potential due to just one charge. Okay, moving just a single charge, a unit charge. Okay, to a point. But what if we are looking at the electric potential in moving system of charges? Let's say Q1. Okay, to point A. I have another charge, Q2. Excuse me. Okay, Q2. Let's say I still have another charge. Okay, Q3. Okay, let me stop here. And of course, the distance here is R2. For Q1, that's R1. And of course, for Q2, that's R3 from the point A. Okay, so to get electric potential at point A is going to be potential due to all this system of charges Q1, Q2, Q3. So I'm going to sum them. Okay, so the total electric potential is going to be the electric potential due to let's go V1. Okay, potential due to Q1, V2 potential due to Q2, then plus V3 potential due to V3. All right, so now let's do that. We are going to transform our formula, right? Don't forget our formula for potential. Okay, so that's going to be K Q1 all over R1, right? For V2, that's going to be K Q2 all over R2. Then plus V3, I have K Q3 all over R3. Okay, so let's do something about this. Okay, so I can factorize. Simple. K is common in all these 3 fractions, so I can simply take the K out, open bracket. Of course, I'm left with Q1 over R1. Then for this, I'm left with Q2 all over R2. Then of course for this, I'm left with Q3 all over R3. So this is the formula, okay, which we actually apply in if we are evaluating electric potential at a point due to what system of charges. So please take note of it. All right, take note of it. Let's see if there's an example question that we ought to apply. Okay, so depending on the number of charges, you can just apply that, right? Okay, I have an example here, and then let's do justice to this. Let's do justice to this. Okay, here the question goes. The following point charges are placed on the x-axis, 2 microcoulombs, okay, at x, at distance, okay, from the x-axis 20 cm. Then of course minus 3 microcoulomb, the distance is 30 cm, and minus 4 microcoulomb, and the distance is 40 cm. Find the potential on the x-axis. Okay, simple. Okay, so apply the formula. There are 3 of them, so the formula for the potential at the x, okay, is gonna be K, of course, open bracket, Q1 all over R1 plus Q2 all over R2, right, plus Q3 all over R3. All right, so let's go there. So I'm gonna have, of course, you know what our K is. That's gonna be 9 times 10 raised to power 9, right? Open bracket. What is my Q1? My Q1 is 2 microcoulombs, okay, and the distance is 20 cm. So that's gonna be 2 microcoulombs divided by 20 cm. Then I have to convert that cm to meter. Don't forget. So that's gonna be 0.2. All right. Then plus Q2. All right. Now Q2 is minus 3 microfarad. Okay, because of that minus, definitely that minus will actually, okay, change this plus now to minus, because plus times minus is always minus. So I just do that, okay, immediately. Okay, so I just put the minus, right? So of course the charge is 3 microcoulombs, and I've not been converting the coulombs. Please pardon that mistake. Is very important. You need to convert the coulombs, the microcoulombs, okay? You need to convert the microcoulombs, okay? So here I now have 3 microcoulombs. 3 times 10 raised to the power of minus 6 divided by the distance is 30 cm, right? So 0.3. Then of course the next one is it minus, yes, the minus 4, and this 40 cm, minus 4 microcoulombs. Okay, divided by 0.4. Okay, you know how we do this, okay? So this is gonna be 9 times 10 raised to the power of 9. Okay, I work with this 2 divided by 0.2. This should give me 40. Right, this is what? No, not 40. Please pardon me. This gives me 10. Let me do that before I get confused, okay, with just one simple calculation, right? Okay, so now it's 10. Please pardon me. All right, so now I'm having 10 times. There are many ways you can do this, okay? Just use the method that's convenient for you, okay? So I'm just doing my own thing. This is also gonna give me 10. This is still gonna give me 10. Okay, and this is still gonna give me 10. All of them are 10. Okay, And of course, this cancels this, okay? So I'm left with this minus 10, okay? So I can now use 9 to multiply this. That's going to be minus 90, all right? Then 10 raised to power. 10 raised to power 9 times 10 raised to power minus 6. That's 10 raised to power 3, okay? Yep. That's going to be minus 9,000 volts. Okay, so you can spell, of course you can just try this, see if I made a mistake, okay? But importantly, you know the formula, you know the procedure. That's all. All right, so here we go. Can we proceed? Okay, so now I have another question. Let's work on this. All right, so it's not complete. Let me complete the question. Okay. Okay, so yeah. Okay, so nice. I'll now bring the complete part of the question. Right. Here we go. So kind of long, so but we'll definitely deal with it. Now find the electric potential at point A and B due to two small spheres X and Y 1.0 meter apart in air and carrying charge of 2.0 times 10 per minus 8 coulombs minus 2.0 times 10 per minus 8 coulomb respectively. Okay, assume that the permittivity of air is this 9.0. Of course, there's a constant. Okay, all right. Okay, well, the important thing is that they just give us the constant. All right, so now this is the diagram. Okay, let's say as shown, and of course such a question, there's a diagram that actually, so you look at the diagram. Okay, this is the diagram of kind of, so now let's go back to the question. Okay, now find the electric potential at point A and B. So I go to the diagram. I have point A and B. So I'm looking at electric potential at this point A. Okay, let me emphasize on that. Please pardon me. Let me emphasize on that. So this is the point A. And so we're looking for electric potential at this point. And of course, you don't need someone to tell you how we are going to sum the potential, okay? If you want to sum the potential on point A, because the charges according to the question is found at S and Y, all right? Of course, they due to two small spheres, S and Y, okay? Which is 1 meter apart in air. Okay, so the charges is due to the charge X and Y. So we're looking for electric potential at point A first, because the question is in 2 dimensions. Looking for electric potential at point A. So if I'm looking for the electric potential at point A, is due to the charge, okay, the charge at X, then plus the charge of Y. Okay, so the sum of the potential of X and Y, that gives me that of A. Then if I'm actually looking for the potential at point B, the same thing. Okay, here, then here. All right, so let's start with the very first. Okay, the potential at point A, so VA. So if I'm looking for VA, of course that's gonna be the sum of Vx, potential of X, okay, due to X, then potential due to Y. Of course, let's go there. That's gonna be K. All right, Q, let's say X, right, divided by the distance of X, okay, Rx, plus K QY. All right, of course you can take the K out, right? It doesn't really, okay, the K out. Of course, here this is gonna be okay. Here we go. Y, right? That's our formula, right? Okay, so now let's go there. So let's start solving. That's gonna be k 9 times 10. That's power of 9. Okay, so qx, the charge of x, let's see what that is. Okay, so according to the charge of x is 2.0 times 10 to the power minus 8, and that of y is 2.0 times 10 to the power minus 8. Okay, they are the same. Okay, the two charges are the same. Okay, one is plus, the other one is minus. Okay, okay, so this one is plus 2 times 10 raised to the power minus 8. And of course, the distance from the x to that point A is 1 meter. Then of course, plus the other charge is negative. Okay, that will make this to be minus. Plus times minus is minus. Okay, and the charge is 2.0. Right, this one 2.0, right, times 10 raised to the power minus 8. Now, what actually the distance would be different. Remember, the distance is going to be the distance from x to A. Okay, the distance from y to x is 1 meter. There, 1 meter plus this 1 meter, so that makes it 2, right? So the distance is 2 here. All right, so let's go there. Here we go. Open bracket. If I divide this by 1, I'm still gonna have the same thing. And if I divide this by 2, 2 cancels 2. So I'm left with just 10 raised to the power minus 8. Okay, so of course, if I should actually factorize this, I can take 10 raised to the power minus 8 outside. Yes, factorization. Simple. Okay. 10 raised to the minus 8 is common here, so I can take it as a factor outside here. 10 raised to the power minus 8. That's how I solve. But in case you can do it different way, but make sure you have the same answer. Okay, so now since 10 raised to the power minus 8 being a factor is already outside, okay, so I write the 2 that's left here, and of course what is left is 1 because 10 raised to the power minus 8 is already outside here, right? That's 2 minus 1, so 2 minus 1 is 1, and of course 1 multiplied by this multiplied by 9 will give me 9, and that will gonna be 10 raised to the power of 9 minus 8, that is 1. Okay, so that's simply 90 volts. VA is 90 volts. VB, the same. VB, we still have the same thing. Okay, the same VX, V due to X, V due to Y. Okay, so let's go straight to solve that. Okay, don't forget the formula. That will be K QX RX plus QY RY. Okay, so let's go there. 9 times 10 raised to the power of 9. Of course, this is 2 times 10 raised to the power of what? Minus 8, right? Divided by the distance, which of course now distance has changed now because we are considering B, that's 1. Okay, it's still 1. Okay, this is 1. All of them are, they're 1 1. So 1 minus 2 times 10 raised to the power minus 8 divided by some 1. Okay, this divided by 1 is to give me this, so this definitely, this minus this is 0. Okay, when you subtract it, they are the same. If you subtract it, it will give you 0. So and 0 multiplied by this is 0. So the potential at B is simply 0 volts. So I hope that is well understood. That's electric potential, right? So now let's go to the next subtopic. Okay. Okay, so what we are going to be looking at now is electric potential difference, right? Electric potential difference. Here we go. Now let us write down the amount of work done in bringing a unit positive charge from infinity first to a point A. Let's say you move to point A from infinity, okay, and then you now move to point B. So that's potential at point A and potential at point B, okay. So now the difference of these two potential between B, okay, from A, difference in mathematics is minus, okay. The difference in potential of point B and point A, since you move to point A and point B, okay, is work done in taking the unit charge from A to B, okay. So that's what they call the potential difference, the difference between the potential of 2 points, okay. So let's say you have point A, okay, you move a charge to point A, which gives you a potential VA, okay. So you move it again to point B, we take VB, okay. Okay, so we are considering from infinity, from this point, because this A is from this point to this point, okay. This let's say this is where the charge is coming from, okay, and this B is from this point, though it goes 2 places, okay. It's from this point to this point, okay. So that means between here and here is what is known as potential difference, okay. So between point A and point B is known as potential difference, VB minus VA, okay. That's potential difference. So how do we do that, okay? So we'll first evaluate the potential of B, that is VB first, okay. Of course you know that VB by our formula, okay, and of course we are considering just a charge, okay, just the charge Q. So that's gonna be K, okay. Let's say Q, then of course the distance, okay. Let's say the distance of Q to that B is RB. The distance Q to A is RA. Okay, so now, so V is going to be KQ. Then, of course, sorry, the B, I'm doing the B first, okay. KQ, then RB, the distance. Then minus, I do the same for A, okay. The same KQ, the same charge. Then distance, which of course is RA. Okay, so with what we have, okay, you know very well that we ought to factorize. We definitely ought to factorize. K is taken outside the bracket, of course, we are left. Of course, Q is also common, okay? So I'm taking both KQ. Q is common, okay? So what is left now is 1 over RB and 1 over RA, okay? So this is what is known as electric potential, okay? Electric potential difference of A and B, okay? And it is this difference that will tell you the work that is done in moving this charge from this A to what? This B, okay? Because between this A and B, the work done in moving the charge from A to B, okay? So please take note of that. All right, do we have question that we ought to apply? I think I have something, okay? I have something here that's kind of that looks somehow complex, right? I will bring it to the screen. Okay, so here there's a diagram here, okay, if you can see the diagram, but let's look at all these arrows, all this line represent electric field, okay, all these are electric field. But let's look at the question. So compute the potential difference between point A and B, assuming that a test charge Q0, okay. Let's say the test charge, this is a test charge, this is where it is Q0. Let's analyze the diagram, okay. So a test charge Q0, okay, let's go to the question. Q0 is moved from acceleration from A to B, okay. So that's a test charge Q0 is at C, okay. It's moved from, okay, so it's moved from where? From A to B. It's moved from A then to B, okay. So now that is, for me to get the difference in potential of A to B, I need to get the potential at A. You know that already. Potential at B, then I now subtract it, okay. You know our formula. Let's now go to our formula. So the potential difference, VD, okay. Let me use VD to represent that, okay. All right, it's gonna be equal to another formula, okay? KQ open brackets 1 all over the distance of, okay, B minus 1 all over the distance A. How do we get that distance? Let's go back. Okay, though no distance was given to us, okay, but we know that the distance from A to B is D, according to this diagram, okay? According to look at this D, okay? So the question is, how do I use this D? And of course, the angle here, the angle, let me draw this very well, okay? So let's say I join this. This is right angle triangle, all right? Right angle triangle. And this is angle 45. I need to get the distance from this Q to B. That will give me, that's this, okay? And of course, this distance from BC, this is also, this is from A to this point, okay? Still BC, okay? Now, how do I get that? Remember, what I have is, okay, better still, for me not to, okay, get you confused. Let me use the triangle inside, okay? So if this is 45 degrees, okay? Remember, the whole of this is 90 degrees. So the triangle inside, the angle inside here, okay? The angle from here to here is going to be 90 minus 45. That'll give me 45 degrees. So what's the whole idea of this angle, okay? Since this length has been given, which of course is D, which is of course the opposite of this right angle triangle, okay? For me to get BC, remember BC, okay, becomes the opposite here. This is where the angle is. So the BC becomes the opposite of this right angle triangle because it's opposite to this angle, okay? Then of course the hypotenuse becomes CA. All right, remember my difference, I need to get my BC and of course CA, okay? So how do I do that? Having my D, okay? Remember, I'll use ratio. Let me do that beside here, okay? Don't forget, if I want to get my BC, BC is opposite, so I'm going to use sine, okay? I'm going to use sine 45. Sine 45 is always opposite all over hypotenuse, okay? Okay? Now, okay, I'm not using sine 45. Remember, what I have is D, which is adjacent. Please pardon me, okay? All I need is to use is tan. Because I have the D that I have is the adjacent, and of course the BC I'm looking for is the opposite. So I'm using tan. Tan is opposite all of adjacent. So I'm going to have tan 45, all right, which of course is going to be equal to BC, the distance I'm looking for, okay? Because I need BC, then divided by the D, all right, the distance, the adjacent. So BC, distance BC is going to be equal to D, if I cross multiply, right? D tan 45. I am done with my BC. Let's get our distance AC. AC is the hypotenuse, okay? Hypotenuse and adjacent, that is cos theta. For me to get AC, I'm going to cos 45, right? Of course, adjacent. All right, adjacent is D. All right, adjacent of that triangle is D, okay? All over the hypotenuse, which of course is AC. That's what I'm looking for. So if I rearrange this equation and I have that my AC, okay, is going to be equal to D. All right, all over, if I rearrange my equation, right, cos 45. Okay, remember this question didn't give us any value, okay? It only gave us this angle and D, okay? So that's what we are going to make use of what we have to get our potential. Now let's go to our potential, right? Don't forget our potential difference is going to be equal to KQ, right? So I'm very sure that since we are actually solving this, no value was given, okay? No value. So it's going to be just in terms of formula. So I can just, no need to put the value of my K, I just allow it that way, okay? And of course the Q is, they say it is, the Q here is, they called it Q0. So I'm going to change it by the symbol they gave me, which of course is Q0, right? Then open bracket 1 all over RB. Don't forget my B, okay? Okay, this is it. By B is the BC. the distance of, okay, this arrow B, don't forget, from B to C. And of course we did that, and that gives us D tan 45. So that's going to be 1 all over D tan 45. All right, then minus 1 all over RA. Let's check that out. Of course, what I got as my RA, okay, is definitely is the AC, okay. The RA is the AC from C to A. That's the distance, okay. D all over cos 45. Bracket closed. Of course, this is reciprocal. They call this particular fraction reciprocal. 1 all over a fraction, okay. It's reciprocal, so I can invert it. So my final answer now can be KQ0 open bracket 1 all over D10, okay, D10 tan 45, right, minus inverse cos 45 comes up, cos 45, okay, all over D. Okay, I think there's something else that can be done to this. Okay, I can still simplify this this fraction here. Okay, I believe I can still factorize that fraction there, but I don't want to go through that process. You can do that. Okay. All right, so please take note of that. I just illustrate how you apply the formula of electric potential difference. Okay, so please take note of that. We still need to solve questions, but then let's actually look at the next subtopic. All right, so here we've done. So now we are going to be talking about equipotential surface. Let's look at the surface known as equipotential surface. Okay, now let's go. All points in a field which have the same potential can be imagined as lying on the same surface. Okay, so we can simply call that equipotential surface. So we define the equipotential surface from what we have here is that is the point or the point on a surface that have the same potential. The word equi means equal. Okay, so combining the two, equipotential is equal potential. Okay, point on a surface that have equal potential. So which simply means that if I have a surface, let's say this is a surface, okay, or let me, okay, that has different potential at each point. Okay, let's say this point A, this point B. Okay, so it simply means that if this potential at point A and point B, okay, of course the potential at point B, let me call it VB. Potential at point A, that's VA. All right, so that should tell you that the potential difference between them, okay, that's VB minus A, okay, is just going to be VB, Abi, minus what? VA. And of course, since they are equal, okay, when you subtract it, will give you 0. So 0, okay. So we simply mean that the potential difference, okay, that you have in a potential surface is always equal to 0, okay. So, and if there's no potential, what actually causes work to be done if there's potential difference? So since potential difference is what the potential difference is 0, okay, take notes, okay, the implication is that in an equipotential surface, no work is done, okay, in moving a charge, because work is based on the potential difference. Potential difference is 0, work is 0, okay. No work is done in moving charge in equipotential surface. So please take note of that. Equipotential surface, in as much as electric field is concerned, is a surface, okay, is surface that each point on that surface, all right, have the same equal or have equal potential. So please take note of that, okay, as we probably check if there's another thing. All right, think of finally we gonna look at a very important relationship, okay, that we ought to, right? So now before then, there's one question that we need to evaluate, but then, okay, I will, okay, so let me just give a break, okay? So I need you to digest this. then I will just come up again, then we'll continue. All right, see you. Hello, you're welcome back. All right, so now we are gonna continue from where we stopped. Okay, so now previously we actually looked at electric potential, and we have also we talked about electric field intensity. That's when we treated uh, electric force, electrostatic force. All right, so now we're going to look at the relationship between electric field intensity E and electric potential. Okay, what formula connects these two? All right, so that's what I'm going to be looking at here now. All right, now let's look at how we derive that relationship. Now we already know that electric potential, okay, is giving us the work done per unit charge. Work per unit charge. Okay, now, and we already know that work is force times distance, right? Force times distance. Let me use D this time around, okay? Force times distance, then divided by charge. And remember when we treated electric field, we said that electric field is the force experienced by a unit charge. Remember that? Okay, let me write that. Remember, okay, remember this. Electric field intensity is force, electric force per unit charge. So if you look at that in this formula, force all over Q is E, okay? So I cannot replace this. So invariably, I can simply say that, okay, electric potential, okay, is related to electric field by, from here, we now know that F all over Q is E. So that will give me ED, all right? So electric potential is equal to electric field multiplied by the distance, okay, between the two charges, between the point, okay, and of course the reference. All right, so please take note of this. Okay, so this is the relationship, and we are going to look at question that will help us understand this better. Okay, we're going to apply this. Okay, so now I pick question. Okay, so I bring it to the screen. Okay, here we go. Okay, so now, so the question goes like this: two large horizontal parameter plates are 20 cm apart. So the distance between them is 20 cm, and of course it's in air. Okay, and the upper is maintained at a positive potential relative to the lower, so that the field strength between electric field strength, which is something as the intensity, right, between them is 2.5 times 10 raised to power 5, right, volt per meters per meter. There's another way of, okay, there's a unit of electric field in intensity, volt per meter. Okay, of course you know that if we have V equal to ED, then another SI unit for electric field intensity is going to be, okay, volts per meter. V is volts, D is meter. Okay, so this unit is consistent. The unit here is consistent with this formula. All right, so now let's get to the question proper. So what's the question? The question is, what is the PD between the plates? B, if an electron of 1.6 times 10 raised to power minus 19, okay, coulombs and mass, okay, that's not, but let's solve this first. All right, so the question is, what is the PD between the plates? So very simple. So solution, okay, so according to the question, right, we have been given the E. The electric field strength or intensity is still the same thing, and of course that value is 2.5 times 10 raised to the power 5. So 2.5 times 10 raised to the power 5, right? Volt per meter. All right, so now, okay, and according to the question, the distance between the two parallel plates is 22.0 cm. Okay, so that's the distance D. Okay, 2.0 cm, which of course I need to convert to meter, which gives me 0.02 meter. Okay, so let's now, what are we looking for? We are looking for the electric potential difference, V, okay, between the two plates, right? Here we go. So apply the formula. Remember, V is equal to ED. I've already derived this formula, right? So this is gonna be equal to, what's my E? My E is 2.5 times 10 raised to the power 5, right? Multiply by the distance, which here of course is 0.02. So if we do this multiplication, right, this is gonna give me 5, because 2 times 2.5, okay, that's 5. Now I have 0.0 before the 2, okay, so that's, I can naturally subtract it from this powers of 10. Okay, if you know how to do standard form, or better still, if you can't do this way, just do the way you, okay, just 2.5 times 0.02, then simplify and get your answer. Okay, so any method that is convenient for you, you just do that, right? So now, so I'm gonna 0.02 subtract it from this 5. That's, I'm gonna subtract how many decimal places that? That's 1 to 2 decimal places, that's 2 from the 5. So I'm gonna have 5, okay, times 10 raised to the power of 3 volts. So that is the first part of the question, right? Okay, so let's look at the second part. Of course, that's the second part of the question. The B part is not complete, so let me get the complete question, right? Okay, so here we go. Let me get a complete question, right? Here we go. Okay, so now the B parts of this question is that if an electron of charge 1.6 times 10 raised to the power minus 19 coulomb, okay, and mass 9.1 times 10 raised to the power minus 31 kg is liberated from rest at lower place, what is its speed? Okay, so we're looking for the speed of the electron. So the speed, so how will I get speed? That's the question. Okay, how will I get speed? Now, speed of an electron, we can get it from the kinetic energy of the electron. So how does kinetic energy relate to all that we are actually doing here? Okay, now let me tell you how it's related. Okay, already you know that potential difference, okay, V is the work, all right, done per unit charge. Okay, so, and the work, if I should cross multiply, that will give me VQ. Please take note of this. Okay, all right, work and energy, they are the same. All right, work, okay, is also equal to energy. Why? Because they are measured in joule. In fact, energy is the ability to do work. Okay, so if you have an energy, so which simply means that the kinetic energy of this electron is still the same as the work, okay, which is of course the voltage, the potential times the charge. All right, so now let's do that. So the potential energy, the energy, okay, of course, call it potential energy. So it is the potential energy of, which is equal to the work, is what is converted to the kinetic energy. Okay, conversion, the potential energy converted to kinetic energy, have mv squared, right? So our formula now is going to be VQ, voltage, potential times charge, is equal to half mv squared, okay? Because it is this electric potential, which is the work, multiply the charge, okay, that was converted to the kinetic energy of the electron. So now let's actually solve this. So what is my V? I have actually evaluated my V, and this is what I have, 5 times 10 raised to the power 3. So this is gonna be 5 times that, 5 times 10 raised to the power 3 multiplied by the charge. That's the electronic charge, okay, which of course the value was given to us, an electron of charge 1.6 times 10 raised to the power minus 90. So this is going to be times 1.6 times 10 raised to the power minus 19. Okay, it's going to be equal to half the mass. Okay, what mass are we having? 9.1 times 10 raised to the power minus 31. All right, then times the v square. Remember, that's what I'm looking for, velocity, which of course is the speed, okay, v square. All right, so now let's work on this, okay? So I'm going to multiply the whole of this across multiplying this across multiply, then divide by this. That will give me v square. So invariably now I can simply say that my v square is, first of all, the cross multiplication of 2 times this. So that's going to be 2 times 10 raised to the power of, okay, sorry, 2 times 5, okay, pardon me, 2 times 5 times 10 raised to the power of 3, raised to the power of 3, okay, times 1.6 times 10 raised to the power of minus 19, okay, is the cross multiplication. Then of course I now divide it by this, okay, that gives me the V. 9.1 divided by 9.1 times 10 raised to the power of minus 31. Okay, so I think we need the help of calculator. All right, so we're going to calculate that. Okay, here we go. So you know how I do that. I multiply 2 times 5, that is 10, 10 times 1.6, that is 16, okay, then I now divide the 16 by 9.1, okay, so that's what I'm going to do. 16 divided by 9.1, what do I have? 1.7, so I'm having, okay, 1.8 approximately, okay, 1.8 approximately. So I'm having okay, as v square is equal to, okay, let me approximate it, 1 point, let's do it this way, 1.76. I hope you're with your calculator, okay, it's better at 2 decimal place, 1.76. Then of course multiply by the powers of 10. Remember, okay, how I normally evaluate the powers of 10, okay? For the multiplication, I will have to add the powers, right? I add this, that's gonna be 3 minus 19, okay? Then for this at the numerator, okay? For this division, it becomes minus, because minus into minus 31, right? Okay, this was 3 minus, because this was supposed to be 3 plus minus 19, that gave me 3 minus 19, okay? Then of course this division now makes, is what brought this minus here, right? Then of course minus the power in the denominator. So I hope that is well understood. Okay, so this is going to be v square equal to 1.76. So let's subtract all that. Okay, of course, minus times minus is plus. Okay, so what I'm having here now is gonna be 3. Okay, minus 19, then plus 31. That's 15. 10 raised to the power of 15. All right, so now that simply means that if I want to get my V now, I have to evaluate the square root of this. You can decide to multiply 10 raised to the power of 15, okay, or you can do something like this. Okay, you can just reduce this, okay, push this decimal point forward to give you 17.6. Why did I do that? So that this can now reduce to, because I've increased this decimal point, so this can reduce to 14. So when I want to find the square root, okay, I can just find the square root of powers of 10. Simple, divide the power by 2. It's easier. So I need to make it an even number, okay, so that I can divide it by 2 to have an answer, right? Okay, so my answer now becomes, okay, is equal to the square root of 17. Let's 17, okay, 0.6 squared. So that's gonna be 4 point approximately, okay, 4.2. Then multiply by, I'll find the square root of 10 raised to the power 14. To find the square root of powers of an index, divide the index by 2, okay? So that's going to be 14 divided by 2. So that's going to be 10 raised to the power 7. Okay, don't forget the SI unit of velocity. It is meter per seconds. All right, so I hope that is well understood. Okay, so I'm very sure by the time you look at this again, you will definitely get it. Okay, so, and of course you should also take time and learn standard forms, decimals, and of course anything that has to do with powers indices. Okay, because electrostatics calculation, okay, deals with a whole lot of standard form. All right, so you can actually learn that, because that should be, if you are finding it very difficult with this calculation, okay, that your problem possibly is with standard form. All right, so you should go and of course learn standard form. Okay, so I think that is that for this topic. All right, let me see if there's another question I can do justice to know. Okay, if there is, okay, that will be in the next video. Thank you very much. Hello, you're welcome back. All right, so now we are gonna continue from where we stop. Okay, so the previous